It's time to complete the code of this Nsumo robot, finally. In the last video, I sketched out the state machine diagram and wrote the corresponding skeleton code for it. And in this video, I'm going to finish it up by filling in the details and confirm that it works, first in my simulator bots2D and then on this actual robot. I'm going to begin by setting up the simulator, and as I told you previously, I use a simulator to save me time during development, because developing directly on the target is quite tedious when you are dealing with the microcontroller, because then you have to flash each change to the microcontroller. The idea is that I can use the same application code on my actual robot as I do in the simulation, and only replace the lower layers that are specific to my microcontroller. And this means that if I get the application code to work in the simulation, it should also work on the actual robot. So I can spend all of my time developing the application code using my simulation before moving on to the robot. I already presented and spoke about my simulator in a previous video, so go check it out if you haven't watched it. But in that video I didn't actually show how to use it, and that's what I'm going to do in this video. My simulator bots2D is available in a Git repository on GitHub, and what I'm going to do first here is I'm going to clone the repository. I will clone it recursively since it has a bunch of Git submodules inside it. And now once it's cloned, we can have a look at the README, where there are more instructions about how to actually use it. And to build it, you will need to install some additional packages, most likely. And these are the packages you need if you are on Ubuntu. I have already installed these on my machine, so I don't need to do it now. And then to try it out, we can have a look at the test application, which I've added to the repository. So I'm just going to change to my development window here. Then we can go to the test app and we can follow the instructions in the README. I should create a build folder and then I should run cmake to build the test app. That's what I'm going to do. Let's create a build directory. Go into build directory and then build. And then I can open the test app. And here is the test application. There is a bunch of scenes that I can go through here. I already showed you this in the previous video. The scene right here is basically the scene that I'm going to recreate using the new Nsumo bot code that I've written in this video series. Since I can build this now, I can close it down. And then the idea with bots2D is that it's meant to be used as a framework. So it's meant to be used in a way where you create your own application and use bots2D as a framework. So that's what I'm going to do right now. I'm going to create a new application, which I'm going to call Nsumo app. And then I'm basically going to mimic the test application, which are already available in this repository, the test application that I just ran. And inside this application is going to be a bunch of code, or a bunch of glue code that's going to glue the application code running on this Nsumo bot together with the simulation code in the simulation framework. So there's going to be a bunch of new files containing C++ classes and so on. It's fairly straightforward because I can mimic the test application, which is already available. And the reason I've designed like this is because I want bots2D to be a simulator that you configure and adapt through code rather than a limited and fancy graphical user interface. So looking inside at the files available in the test application that I'm going to mimic, there is a bunch of files here, and since this application is a standalone C++ application, it's going to first of all need a main function. So it's going to need a main file. Let's begin by creating that. And the main function is essentially just going to initiate the application class, which I'm going to create soon, and then run it. And then I can go on to creating the... Oh, I should, of course, move this to Nsumo app. And then I can move on to creating the application class, which is going to derive from a base application class from bots2D. And that's going to be similar to the application class inside the test application. So let's have a peek at that. Then I can also open or create corresponding files for my application, or the new application. I'm going to call that Nsumo app. Then I can essentially mimic the test application. I'll be a header file first. I will have a class deriving from the base class. I will write a bit of C++ code here in this video, which I haven't done in the other videos in this video series, since on this microcontroller, on this Nsumo robot, I've only written C code, and I'm not going to talk about C++ here. So if you're not used to seeing C++ code, bear with me. I'm soon going to get to the point where I start writing C code to finish up the state machine code. I also need to include. Then I can switch to the implementation file and also look at the implementation file for the test application. And there is mostly just going to be boilerplate. I'm going to keep this application simpler than the test application, because here in test application I have multiple scenes, but in the application I'm creating now I'm just going to have a single scene which I will use to simulate my Nsumo robot. But in a similar manner, I'm first going to implement the constructor and give my application a name, Nsumo app, and then I will register the scene that I will have in my menu and also set that to my default scene like this. Then I will have an empty destructor and two other functions that's also going to be empty, but which I have to overwrite. This class is essentially not doing anything, or it appears to do nothing here in my file, since there is essentially no code, and the reason for that is that most of the application is inside the base class that I'm deriving from. Okay, then I can continue with creating the scene, which is going to contain my Nsumo robot. So I'm going to have a folder for that, scenes, and then add Nsumo's implementation file and a header file. And this scene is just going to be another C++ class. Beginning with a header, I can have a look at the Nsumo bot scene inside the test application. First, define. And then this class is going to derive from a base class called scene. And as other classes, it's going to have a constructor and a destructor. And it's going to have a function, it's going to override, called onFixedUpdate. Same as this scene here. Copy that, and then it's going to contain a bunch of assets, and this scene is going to contain my Nsumo robot, the simulated Nsumo robot running the application code, but I'm also going to have an opponent Nsumo robot which I can control with my keyboard, and then there is also going to be the platform which the two Nsumo bots are competing on. But I will begin by just adding the platform and the keyboard control Nsumo robot, just to see that I can compile and so on. It's going to be these three objects here, which means that I also need to include, so they are available, or I'm actually going to forward declare here, and then include inside the implementation file instead. Going to be Duhio, Nsumo bot, and controller, and then I also need to include, and then I can switch to the implementation file of the scene. Also have a look at the implementation file of the scene in the test application. I can begin by including scene, and then I can create a constructor which is going to be similar to the constructor in this file. That's going to be Nsumo scene. Then I need to provide some arguments here. I need to provide a description for the scene, and whether it's going to be physics viewed from above or from the side. And for this simulation I will have a top-down view. And then I also need to pass the update frequency that I want. I'm going to update 1000 Hz, 1000 times per second. Then I can first create the platform in this constructor. So how big it is and what kind of texture I want for it. Then I can create the actual object, same as I do in the test application. So I can copy that. And after that I can create the opponent, the Nsumo robot, which is going to control with my keyboard. We'll call that M4 wheel bot opponent. So in bots2d there are already assets available, so to create this Nsumo bot I just pick one of the available blueprints or templates, which is for this four-wheeled Nsumo robot, and here I give the start position and the orientation where this Nsumo robot should spawn. And after that I need to say how this robot is going to be controlled. So I need to create a controller component, a keyboard controller. Also set this controller component of the Nsumo bot object, but this keyboard controller is actually not available in among the assets, so I actually need to create a class for it up here. And I have already created it here actually. So what I'm going to do is to simply copy this keyboard controller from here and paste it. So what this controller is doing is that it's taking the inputs from the keyboard and then translating that to corresponding voltages that should be set to the individual motors. Just a bunch of if-else on the specific keyboard event and then setting the corresponding voltages for the motors. And then I also need includes here. And I should put this inside a namespace just for good practice. Yes. Okay. And then to build it, I'm going to use CMake because that's what I use in Bots2D. So I need to create the CMake lists file. And I'm simply going to mimic the CMake file inside the test application. I won't talk about CMake, so I'm just going to copy the pieces that I need. These are the things that I will need. I will have to add the assets that I'm depending on, and also some of the things that I depend on from the simulator framework, Bots2D. I'm sorry if I'm rushing through some of the details here in terms of the simulation and C++, but I really don't want this video to be about my simulator or C++. The focus should be on this robot that I've been working on throughout this video series. Let's see if I can build this now. Nope. Now. And then, oh, I got an error. Let's fix that. Inside Nsumo scene. Oh, I should also have the destructor here. And the onFixed update. If I build it now. No. This should be public. Typos. Nsumo scene. And whoops, application H. So what's going on now? It should be capital. I need a semicolon here. Now it builds. And then I can try to run it. Okay, so now I have a Nsumo bot which I can control with my keyboard. Then when I have two Nsumo bots here, one controlled with my state machine, I can compete against my own state machine application by controlling this opponent Nsumo bot with the keyboard. Okay, good. Now I'm going to commit this code to the simulator repository. Commit. I don't really follow the same guidelines inside my simulator project, but I guess I will just follow the same guidelines for these commits that I'm making now. I also don't have any static analysis or formatting for this project, just a simple commit. Then in order to run the state machine code, I also need to create a component, a controller component, which is essentially a wrapper around the C code that connects it to the rest of the simulator. Similar to how I created the keyboard controller to control the other Nsumo bot with the keyboard. What I'm going to do now is to create a folder called controllers, and inside this I'm going to create another folder called Nsumo controller. And then I'm going to clone my Nsumo bot code, the repository. Or well, I'm actually going to add this as a submodule to the simulator project. It's going to be git submodule add bytes.git Nsumo. What I need to do now is create two new classes, which derives from the microcontroller component. That's going to be Nsumo microcontroller.h, Nsumo micro cpp, and doing the same thing as I done in the test app previously. Beginning with the header, I will create this new class, or this is actually going to be the exact same here. So I can copy that and then just change to my preferred styling. This is just a class that derives from this C microcontroller class, which is a component available in Bots2D. And yeah, this is just a simple class that takes voltage lines as an argument. Then I can move on to the implementation file and also open the one from test application. This is also going to be the same. What this microcontroller class requires is the voltage lines, which is the concept I've talked about before, the concept that connects the different components to the microcontroller so that the microcontroller can control the components. That's going to be, for example, the motors and the sensors. And then it also needs the main function that it's going to call. And in this case, the main function is going to call the state machine code, or the state machine run function, which I created in the last video. That's why I'm going to create 2 new files that's going to hold this main function. A header file called mainfunction.h and a main.c file. Then I can, starting with the main function, and also look at the test app once again, because it's going to be the same. That's just going to be main. I can also do the if-def here. I'm starting this main function with an underscore because this is not the real main function, and in a C++ or C program there can only be one real main function. But this main function is going to kind of correspond to the main function inside my Nsumo code. And then inside main.c, the first need includes, and then I'm going to implement this fake main function, and this function is going to call the state machine run code. So it mimics the main function inside the microcontroller project of Nsumo. Then I need to add a header for the voltage lines, and this file will hold just an enum of the voltage lines. These are going to be the voltage lines that connects the motors and the line detectors as well as the range sensors to the microcontroller. This in the simulation kind of corresponds to what is done in the lower layers. On this microcontroller I write to registers because this microcontroller has peripherals which talks to the sensors and the motors. But in the simulation there is no microcontroller and there is no real motors or sensors. They are all simulated. So in the simulator, instead of writing to registers, I'm instead going to set the values of these voltage lines. And since some of the drivers are tied to the microcontroller, in order to simulate, I need to replace these with corresponding simulated drivers. That's what I'm going to do now. And these simulated drivers are going to be using the voltage lines, as I said. I'm going to create a new folder called Nsumo simulated, and inside this I'm going to create these fake drivers. I need one for the motor driver, and these are just going to be implementation files, .c files, since the header files, the interface is going to remain the same so that the application code can call the same interface in both cases. It's just the implemented drivers that I need to modify or provide another implementation for. Then one for the line sensors and also one for the range sensors. And I will also need to provide another implementation for assert as well as trace. And finally, IR remote. Okay. And beginning with the motor driver, there will be a bunch of functions that I must implement. Going to be first of all an init function. And in the case of the simulator, I don't need to initialize anything. This will just be an empty function. Then I need a function to set the duty cycle. And first I'm going to check that the duty cycle is lower than 100. And then I need to switch on depending on which motor driver. There is one for the left motors and one for the right motors. And then I set the duty cycle here, and I set the mode, and I set the duty cycle and mode for the right motor driver as well. That's it for this function. Then I need to create the function for setting the mode. And this one is going to be a bit longer. I'm going to switch across the different modes. Either I can stop, drive forward, or in reverse. If stop, I should set the voltage lines connecting to the motors in the simulation to 0. So if it's the left one, I set the voltage lines for the left motors to 0. And if it's the right one, I set it to 0 for the right motor drivers. And then I need to do something similar for if we're driving forward, but then I actually need to pass the duty cycle. And I will have another function for translating the duty cycle to actual voltage. And here I have a few defines where I make some calculations to get the correct voltage for the voltage lines based on the duty cycle. I won't explain that here, but yeah, it's just the kind of the battery voltage that I expect and then the kind of loss that I expect and so on. And I also forgot to, since here I actually set static variables, because I also want to save the current duty cycle here so that I can reset it to the same value. When I set, for example, if I set the right motor driver, I also need to set the same value to the left motor driver. So I'm just going to add these here. And then I will do the same for the reverse. So like this. It's the same basically, just setting it to negative duty cycle or negative voltage. And finally add a few define. I don't think I need that. I take the same header file as in the actual driver, since they have the same interface. And then I need the microcontroller C bindings so that I get the voltage lines functions. And then I also need to include the voltage lines enum so that I can use the values here. That's it for the fake motor driver. Let's move on to the fake range sensor driver. It's also going to have an init function. And similar to the motor driver, this is not going to do anything, but just return OK. Then I will have a function for reading multiple sensor values. And here I'm just going to get the value of the corresponding voltage line, because the simulated range sensor is just an object that measures the distance in the simulation and then translates that to a voltage line value, so a float value. I also need to scale that so that I get the corresponding range. Then I need to do this for all of the sensors. I should set fresh values to true, because in the simulation the values are always fresh. And then I can return, and finally I need to add some includes, like so. And then the line sensor is also going to have an init function, an empty init function. And then I need a function for getting the voltages or the readings from the line sensors. And I will have a threshold value based on the threshold in the simulation. And I'm going to use the same threshold value here as I do on the actual robot. So that's going to be 700. So anything lower than 700 means that it's detected. And if it's above or equal, it's not detected. Fine. I can set this just to 0. And then here I can check the individual voltages or the voltage lines for the corresponding simulated line sensors. It'll be like that. And also a few includes. And then IO remote. Here I'm not actually going to implement a corresponding driver, but I just need to implement it so that I can compile the project. Technically, I could maybe have implemented something where I send commands using my keyboard, but I'm not going to do that for now. Init, empty init function. And then just a get command function that always returns none. So this driver is as if we have a remote that we never press. And header. That's it for those drivers. And then I need to do something for assert handler, since my regular assert handler is tied to the microcontroller because it traces via UART and also blinks an LED and so on. So I need to do something corresponding here that doesn't tie to my microcontroller. What I do is simply trace that an assert has happened, and then I just get stuck in an endless while loop, so that's easy to detect when an assert happens. And then I also need to add some includes as always, like so. And that's it for the assert handler, and then I can go into the trace. In my microcontroller project, as I talked about in a previous video, printf on a microcontroller, I said that I can't use the standard library printf implementation because it takes too much space. So I use some other external library to save flash space by having a more efficient implementation. But in the case of the simulator, space is not a problem. So here I can just use the regular printf function from the standard library. So that's what I'm going to use. Includes first, then an empty init function, and then the trace function, which is just going to wrap the normal printf function. And then you have to write this kind of code. Okay, that's it for the code that I need to replace in the lower layers to make the simulation run. And now I also need to add this to the CMake list so that it's built as part of this simulation application. These are all of the files that I need. So there's going to be some of the application files, which are going to be the same for the Nsumo and the simulator. But then I also need to add these simulator drivers that I just created. And I need to add that to here. And I need to add some more dependency or include directories. And now I can jump back to the simulated scene and actually add the robot, which is going to be controlled by my state machine code. That's going to be another robot here, which I'm just going to call M for willbot. And then it's going to need the component, which is going to control it, which is going to be the Nsumo microcontroller. Then I need to add a class for that, or a forward declaration. And inside the implementation file, I first need to create the new robot, and I'm going to use a blueprint for this as well, another blueprint, which more mimics my actual robot, and let it have another spawn position. And then I will create the microcontroller, the controller component, which runs my state machine code. And here is where I need to assign or connect the voltage lines to the correct components. And the assignment I will do here need to match up with the voltage lines that I added here. I'm going to make a comment about that, and then I just need to do a bunch of assignment for each voltage line. It's going to be like this. So as you can see, the different voltage lines are assigned to the voltage lines of the simulated objects. So here is for the motor, the line sensor, and the range sensor. One more thing I will do to this robot is I'm also going to enable debug mode so that I can see some additional things drawn. Bugged, true. Okay. Now I can create the microcontroller, and I can pass these voltage lines to it, like so. And then I need to assign this microcontroller to the robot. And finally I need to start the microcontroller, which essentially starts a thread that runs the state machine code, which is a thread running separate from the rest of the simulator application. I will need to add an include here for my new controller as well. And one last thing I will do is that when the Nsumo robot drives out of the platform, I want to disable the motors so that it appears as if the platform is some distance above the ground, which just makes for a more realistic behavior, and it makes it more clear when the Nsumo bot drives out of the platform. So here I just grab the distance for all of the motors, and then I check whether those are, if any of them are outside of the platform, and in that case I simply disable the motor. Okay, now I have the code that I need to glue my state machine code or Nsumo code together with my simulation application. So I can try to build this now. Then make. Yeah, asserting here, so I of course need to include assert and build again. This should be line detected. And this error I get because inside the header file for assert handler I am using this assembly function here, and I can't use that on the host. It doesn't even really make sense to try to get the program counter on a host machine. So here I'm just going to rework this a bit and only have this defined when it's on a microcontroller target. That's either going to be Nsumo or the launchpad. And then I have another implementation when it's on the host machine, like this. I try to build again. Now it builds. Good. And I can run the application again. And once again, I have my robot, which I can control with my keyboard as before. But now I have another Sumo robot here, which is meant to be controlled by my state machine. But as you can see, it's not actually moving. And this is because I haven't finished the implementation of the state machine. So now it's just stuck in the wait state, doing nothing. But now I at least have a simulation scene which works and that can run the state machine code. So I'm going to commit this code now. Oh, first I should commit the code inside the Nsumo project. I'm going to create a new Git branch here. Yeah, I'm going to call that feature complete machine. Then go to format, cpp check. Oh, I need to clone some of the, like that. Now if I run cpp check, it should work. Yes. Okay, so then I can add this, then commit. Yes, then I can go to my simulator project again and add this one and also add the controller. Then I can create a commit. Yes. Now the simulation part is finished, so now I can switch back to my normal Nsumo project and continue with the state machine implementation that I began in the last video. The first piece I need to add is the thing that I call input history, which is a data structure for storing previous sensor inputs. And as I said earlier, I will implement this with the ring buffer, which I extended in a previous commit that I showed in the last video. And to do this, I'm going to create two new files under app called input history.h and input history.c. Then I can open the header file, and input history, or this data structure, is going to have two functions. One function to save a new input, and that's going to take ring buffer as an argument and also input. I'm going to create the input struct here, and this is going to contain the enemy input and also the line, and that's the only input that I'm storing here for now. I could of course also add other inputs, such as the command from the IR mode maybe, but as you can see, this struct takes up more than 1 byte, and this was the reason why I need to extend my ring buffer implementation to be able to take elements larger than a single byte. Then I will forward declare ring buffer here and also add two includes app enemy app line, and inside the implementation file I will have two includes here as well, or I need to add a second function here as well, function called input history last directed enemy. And what this function does is it gets the latest input where the enemy was seen and was at angled direction, so whether we saw it to the left or to the right. And this is what I'm going to use inside the search state in order to determine which direction I should rotate towards. Now back to the implementation file. First, the save function, and when I save an input, I'm going to check whether the input is actually an actual input, whether I see the enemy or detect a line. If I don't detect anything, I'm not going to save anything, and I'm also going to make sure that it's a unique detection, so that if I see the enemy in the front several times in a row, I'm just going to save one entry, and this is just in order to be more efficient about the space usage. So first let's check if there is any input in the ring buffer, and then I look at the latest input, and then I check whether this input is equal to the input that I'm trying to save. And to check whether it's equal, I need another static function here. I check if the lines are equal and if also the enemy position and range is equal. And if they are, then it means the input is equal, and then I shouldn't save it. And then if it's valid input, I'm going to save it to the ring buffer by calling the put function. As for the directed enemy function, I'm going to iterate through the saved input and look for the latest enemy detection that detected an enemy to the left or right. Peek at the head, and then I check if it's enemy to the left or right. And then if it is, I return input enemy. As you can see here, I'm kind of using the ring buffer in a FIFO manner, which is a bit abusive, but oh well, that's what I'm going to do here, because this means that I can have a single ring buffer implementation that I can reuse in different places, so I don't need to have a separate implementation just for this case here, even if that would be more correct maybe, but that's just details. And if I didn't find any such input, I'm just going to return a default non-input. Yes, I also need to add this to the make file. And check whether it compiles as well. Or no, I'm going to make use of it inside the state machine before I compile. I can include it here. Include app input history. Be state machine. This one. I can remove these comments now. To fix it now, I'm going to allocate it here, and I'm going to allocate it similar to how I allocate this data. I'm going to allocate it on the stack. It's going to be a local ring buffer, and I'm calling it input history, and it's going to hold elements of type struct input, and then I will set that in the data, and I'm also going to set it in the common. And I'm doing it here instead of inside the state machine init function, since this has a lower scope. So if I were to do it inside here, it would be deallocated as soon as we return from this function. That's why I have to do it here before I call state machine init. And I'm gonna make it pretty small, since I am running out of space here. This is going to get allocated in the RAM, since it's a structure that contains data that may change during runtime. So it's going to be of size 6. And I found this to be enough when testing. Okay, now I can see if it compiles. It does not. Did I think I forgot include. Yeah, it compiles. Good. I will test and see that this works later. For now it's just enough that I can see that it compiles. Then I can commit this as well. Diff, yes. Shouldn't be anything in state manual. New git add, then commit. With that commit in place, I can move on to the things that I need to add in the state machine. As I said before, in the last video, I implemented the skeleton code, but in reality, I actually did a little bit more than that. So there is not that much more code to implement, but there are a few to-dos that I left in the last video, which is what I'm going to fix now. The first thing I want to fix is the process input function. This is the function that looks at the inputs and then translates that into a corresponding event, which can then trigger a transition. This function is first going to get the input. It's going to be enemy, line, and command. Then I'm going to create a struct input, which I can save to the input history, like so. And note, this is the only place where I get the input for each while loop iteration. There is no other place where I retrieve the input from the sensors. And that's also why it's important that I don't block anywhere in the state machine when it's running, so that this function can get called often to get new fresh inputs. And then I can just go through these if-else here, and I need to go through these in order of priority, because as soon as I detect a match, then I'm going to return a corresponding event, and I'm not going to check the other events. So these must come in order of priority. And the most high priority one is if I get a command from the remote control, because then I should transition directly to the state manual and simply stay there. This is just a debug feature. Then I should check if there is an internal event, if one of the states has posted an event internally. Right now, or in this state machine, there's actually just one place where this happens, and that's inside the retreat state, when the retreat state is done. But this implementation here opens up for the possibility to add additional internal events posted from other states. And then I'm going to take the internal event and return it. Next, I will check if the timer has timed out. And if it has, I should stop the timer or clear it, and then return state event timeout. Then I can check if line is detected, and if so, return state event line. Finally, I can check if enemy is detected and return state event enemy. That's it for all of the events, and that's it for the process input function. Then I can move on to the state, starting with state wait. Here I don't need to implement anything more. This is already done, so I can go to state search, and here I need to fix a few things. I need to first of all make use of the input history to make a smarter decision about which direction I should rotate towards. For example, if the enemy is here and the robot rotates to the right because it, for example, detected the line, then it will lose sight of the enemy, but the enemy is still here. And in that case, it's better if the robot, when it goes back to the search state, that if it rotates to the left instead of rotating to the right, because then it's going to see the enemy sooner. That's the idea with this decision here. I'm going to use input history to get where enemy was last seen. And if it was seen to the right, it's going to rotate to the right. Otherwise, I'm just going to rotate to the left. So if it was seen to the left or if it was not seen at all, I'm just going to rotate to the left. Okay. And before I also forgot to add a comment here, just to make that a bit more clear. And one thing I noticed when testing this again is that it makes more sense to have a lower rotate timeout. So I'm just going to change that while at it. And that's it for the search state. Then inside state attack, I am already finished with this state. So I don't need to fix anything else here. It's done, similar to the wait state. Let's go to the retreat state. Here I have a few things I need to add. First of all, I need to fill out all of the retreat states, the different moves the robot should take depending on where the line is detected. That's it. So as you can see here, there is different states, and these corresponds to the state diagram that I showed in the last video. I can take that up again. So what I've written here basically corresponds to the different moves in each individual state that we may transition to, or each substate in the retreat state that we may transition to depending on the input we get. For example, here is a retreat state where the robot is going to take 3 moves. First, it's going to drive backwards for 300 milliseconds, and then it's going to take a sharp left turn for 250 milliseconds. In all cases here, it's driving at max speed. And finally, it's going to take an arc turn that is not as sharp as the previous one, and then it's going to be to the right instead for 300 milliseconds. Okay, and then I need to kind of implement this next retreat state, which represents the different transitions we're going to take depending on where the line is detected and where the enemy was seen. So if line was detected front left, I'm going to check a few more things. I check if enemy is to the right or in the front. Then I should just go to retreat state align right. If it's to the left enemy, then I just align left instead. And otherwise I just go to retreat state reverse. So that corresponds to this transition over here. Then something similar for front right, but mirrored. Okay, so that's this one here. Then I can do the back left, which is a bit different. So here I check whether I'm already driving in the reverse direction. In that case, I do an arc turn right. Otherwise, I check if the state is arc turn right. This is another case where I should do arc turn right. And otherwise, I go to retreat state forward, so just driving forward. And then I will do a corresponding thing for line back right. And for line front, I check if enemy is to the left or if it's to the right. And if it is, I will drive a line left or a line right to go to this corresponding state. Otherwise, I go to state reverse. And if line back, I simply drive forward, as I'm already doing here. Arc turn right, left, and if it's detected on a diagonal, I'm going to assert. It's a rare case, and to handle that better, I would have to write quite a bit of code. Okay, now of course, when I developed this code for the first time, it was a lot of iterating. I didn't just come up with this from scratch without compiling and testing it in the simulation. But to keep this video short, I'm not going to iterate through it in this video and just write the final solution that I've come up with. On the downside, of course, then you can't really see how useful the simulator is for developing the code, because doing this on the actual robot would take a lot of time and be very tedious, because as I said, then I would have to, each time I make a change, I would have to flash it onto the microcontroller. But when doing it in the simulation, I just need to recompile and start the simulation and see whether it works or not. So don't be blindsided by the smoothness of my coding here. The simulator is useful. And then, as I showed in the last video, I am running out of flash space. And now it's actually getting even worse than that. I'm running out of RAM. So for example, when I do a trace call now with this, with all of the code I have in place now, I am overwriting the stack, which gives quite annoying errors, which means that right now it doesn't work if I have the tracing enabled. So because of that, I will have to go to my makefile, and apart from disabling enums to strings, I'm also going to disable tracing. And I'm also going to add a way to disable IR remote to save me even more space, because IR remote is not critical for the functionality. So then it's going to be until here. And while at it, I'm also going to rename this to IR timer. Since I created a new timer struct for the timer functionality in the state machine, so it's just going to be confusing if this is named the same way. Then also inside here and inside here. Once again, it sucks that my microcontroller is so small that it can't fit my code. If I just had a slightly bigger microcontroller, that would be no problem. Of course, I could probably fit in the same functionality if I didn't have all of the abstractions I have here to make my code more readable and easier to extend. There is always a trade-off between how easy and nice your code is to work with against how much space it takes up. And I also need to go to state manual and if and def. Else unused data, unused. Okay, and in the make file should also disable IR remote. Okay, and now I can build this. Fix the compile errors. Search. It's to be in a separate scope. Good. It compiles. You can also check the size occupied. Yeah, that looks okay. We have 1000 bytes to spare in the flash memory. Good. Then I can go back and see if it works in the simulation. So now if I build the, well, I also have to add the input history file. But now if I build the simulation app now, I should expect to see my microcontroller or state machine controlled robot move around and trying to push out the robot that I control with my keyboard if everything works. So I'm going to rebuild this now. And then I can run it. Oh yeah, I forgot one thing. Since I don't have a remote control, I can't start inside the state wait state, because then we're just going to stay in the state wait state. So I'm just going to make a temporary chain testing in the simulation. State wait, we can do state search here instead. And if I rebuild this, now I run it. Still not working. I figured out what the problem is, and the problem is that I missed a thing in one of my simulated drivers. Inside the simulated motor driver, I had to also add this at the end, so I actually set the mode. So now if I build and run this, you can see that my Nsumo robot is actually moving. So the Nsumo bot with the orange wheels is the Nsumo bot controlled with my state machine, and the other one is the one I control with my keyboard. So now I'm driving against my own algorithm or my own state machine, and I think I will be able to win because it's not that good. But as you can see, wherever I drive, the Nsumo bot controlled with the state machine is trying to push out the enemy. Seems to be working. Yeah. And then as soon as it detects the line, it drives away from it. Attack. It's not perfect, but it's doing what it's supposed to do, which is to push me out of the platform. Just go up here, it's going to push me out. Yep, and then we'll try to keep on pushing me out. And if I go here, it's going to push me again. Okay, then I'm just going to amend the problem that I just found in the simulator driver, because that should be part of the previous commit. And now it's time to flash this code or build this code for the robot and flash it onto the robot instead to see if we can see the same behavior there. So I'm just gonna build, then I'm gonna flash it. My usual setup when flashing the robot. As you can see, it doesn't work so well now because it's running out of the platform and it seemingly don't detect the line fast enough. And That's true, and the reason for that is that the ADC sampling is a bit too slow now, so it's only like checking the line just a few times per second. So I'm going to make a change in the code now to improve on this slightly. Okay, so inside the ADC driver, which I wrote in an earlier video, I sample multiple channels using DMA, and it's running a bit slow here. And I've tried reconfiguring this a bit, and I can't run it that much faster, but I can reduce the sample and hold time one step at least, which seems to improve things. So compiling this again and flashing it. Now it works better. It's still not perfect, but this is how good I'm going to get it in this video series. And now it works acceptably, most of the time at least. It's able to push out the enemy and able to retreat away from when it detects the white border. Then I'm just going to try running this with IO remote as well to show that state manual also works. And for that I will need to change the default state or the start state to state wait again and change the make file to compile with the IO remote included. Then I can flash this again. So now by pressing buttons on the IO remote, I can first make it leave the wait state, and then I can take over control and control it manually by pressing the buttons on the remote control, driving forward, reverse, or rotate in either direction. Okay, now I'm going to do my usual drill of formatting the code, CPP check and building. Oh, I got an error here, and that's because I have to fix one of the test enemy function. Since I'm disabling trace, this enemy is going to end up not used, so I can do it like that. Yeah, everything builds, so now I can commit. As said, I could probably optimize this even further to make the ADC faster and maybe even make the enemy detection faster. But I've had enough with this project now, and it's time to put an end to it. Pushing the branch. The Nsumo, create a pull request. Yeah, all checks passed, so then I can rebase and merge. Good, and then I have a few changes inside my simulator, which I also want to commit. Make list and Nsumo controller. Yes, and for the simulator I don't have any CI or anything like that in place, so here I'm just going to push straight to master. This is it. I'm not going to write any more code in this video series. I have implemented everything I set out to implement, and now I have a working Nsumo robot, a complete embedded system. Is it perfect? No. Can I improve it further? Yes, probably. Will I improve it further? No. I'm sick of this project now. But what I'm going to do besides finishing up this video is that I'm going to create another final video where I sum up some of my thoughts, maybe some improvements that I could have made, and also my general thoughts about this video series. Until then, thanks for watching and see you in the next final video.